Hi, we're Team Neurovitals, and our Capstone project is on the sideline concussion detection system. In this presentation, we'll be going over what problem we were trying to solve, how we went about solving it, and the final solution our team has come up with. Team Neurovitals is comprised of 5 members, and they are Daniel, Han, Peter, Jason, and Moise. What is concussion? According to the Concussion in Sport group, concussion is defined as a pathophysiological process affecting the brain induced by a direct blow to the head or elsewhere in the body with an impulsive force transmitted to the head. Mechanically, concussion occurs when the brain is twisted and/or strikes the skull as a result of an impact directly or indirectly to the head, as seen in the image shown. In ice hockey, concussions account for 2 to 14% of all hockey injuries and 15 to 30% of all hockey head injuries. Thus, there is a need for a system that can measure impacts and alert supporting personnel of players that are potentially at risk of a concussion upon a collision in a contact sport. This solution should be able to be inserted inside a common sports helmet, be able to measure the magnitude and location of the forces from the impact, and notify health officials when an impact threshold has been surpassed. The target market our product is aimed at is for amateur level contact sports, for example hockey or football. Therefore, the goal of our product is to be affordable for consumers and accessible for non-technical users to use and interpret.
After meeting with our product owner, Dr. Golnaragi, we started doing research on any related domains of this project. This was during the first sprint, so we began doing research on other similar products and methodologies to finally come about 4 viable concepts. From these 4 concepts, we created a decision matrix to finally weigh the pros and cons of all concepts and come up with our final design. After we decided to use FSR matrix to detect impact location, we built a 2D pressure pad with 5 FSR sensors connected to an Arduino Uno for concept testing. We placed a water bottle onto the pad and the pressure distribution was later plotted in MATLAB. After a successful test, an orientation tracker was built using a 9 degree of freedom inertial measurement unit, also known as IMU, with an Arduino Nano, followed by a code to process sensor data and to simulate the orientation tracking using VPython. And due to the pandemic, we created mini projects and split tasks for hardware and software. For the hardware side, we concentrated on the build and mechanical components of the prototype, like housing for electronics. We decided to use FSR sensors as our main approach for concussion detection. We found the best possible way to incorporate this was by using an FSR matrix and IMU sensors into a 2-cap. And for the software bit, we created a mobile application to communicate with the device. This would serve as an alert system to alert the user once concussion is detected. The tasks were to create a mobile application that could connect to the device through Wi-Fi and using a nice user-friendly interface. Once this was completed, all the components were connected together to form the final prototype for testing.
The Android app that is included with our sideline concussion detection system will detail impact information and notify the user if the impact threshold has been surpassed. The app shows the player status, the measurements from the impact, and the calibration status of the system. A 2D representation of the location of the impact on the head can be seen in the color mapping screen, and once the user has finished assessing the information, the user can then clear the state of the app. In the color mapping screen, the user will see the International 10 to 20 system, which is an established method to describe and apply scalp electrodes to the head of an EEG exam. The purpose of its use here is to allow the user to correlate the impact location with the region of the head that is typically monitored in the context of EEGs. A marker is used to visually locate the impact location. Additionally, the user may return to the main screen at any time to review the resulting impact information again.
The other big part of this project is the communication part. Communication is important because it allows the user to receive alert in real time as soon as an impact is detected. It also allows for a collection of the impact data. The Android app and the device we designed are the main components of our communication system. The Android app uses a TCP server socket to constantly listen for an incoming connection on a specific port. When our device detects an impact, we will utilize a Wi-Fi module to connect to our app using the phone's IP address in the specified port. Once connected, our device will send the impact data to the app and then disconnect. The app will then update the UI accordingly.
We incorporated two types of sensors into our design. The first was the 9 degree of freedom IMU, also known as inertial measurement unit, to calculate rotational acceleration of the head upon impact in 3 axes, so basically in 3 dimensions. The second was an FSR, also known as force sensing resistor. We incorporated an FSR matrix, which would estimate the magnitude and location of impact to the head.
We choose EVL rechargeable 9-volt Li-ion battery to provide power to the system. Higher current draw from the Li-ion battery and rechargeable battery is eco-friendly are the reason why we choose this. In the power system, the Arduino board is directly connected to the battery through a toggle switch. The IMU requires 5 volt to run and powered by the Arduino board. Due to the 3.3 volt on Arduino board cannot supply sufficient current, so the Wi-Fi module powered by the battery through a 3.3 volt low dropout regulator and is controlled by the toggle switch.
The assembly was assembled based on our final design, and as shown in the figure, the 5 FSRs were hot glued to the silver inner tube at the front, top, back, and the lateral positions. A second layer of black tube was then added to protect the FSRs. Extra helmet replacement foam were added at the front, top, and back positions to help the FSRs better contact with the helmet. The main housing was 3D printed, and it contains a 9-volt battery, Arduino Nano, and a Wi-Fi module. The user can still get access to the Arduino's USB port for software updates or debugging. A neck tube was made to hold the main housing, whereas for a final commercialized product, a better design should be considered. The IMU housing was also 3D printed, and it was attached to the top of the helmet using adhesives. The photos show the front and back views of the final assembly. The top view shows how the IMU housing was attached and wired to the main housing. Note that we only use jumper cables for prototyping purpose. Thus a better wiring must be designed later for the final product. Next, we'd love to present a pre-recorded video as our prototype demo. Before starting the system, please ensure that the phone and the helmet are under the same Wi-Fi. If the app shows not calibrated, don't worry. Simply detach the IMU housing and move it in an 8S-shaped pattern. This will calibrate the magnetometer within the IMU. Once your app shows calibrated, you are good to go. Next, I'll demonstrate how the FSR matrix can estimate the impact location and magnitude. As you can see, I stroke the front of the helmet. For the purpose of this demo, the concussion threshold was lowered so that the system can respond to my strike. To see the location of impact, tap the color mapping button to see the green impact marker. Once you're done viewing the impact information, you can tap the clear state button. Now, I'll strike the left side of the helmet. Due to the deep sleep mode of the Wi-Fi module, there is a small delay in warning. Once again, you can check the location and clear the state. Then, I'll strike the back of the helmet. Again, the app updates the new impact location. Finally, I'll strike the back right zone of the helmet. Once the app receives the latest warning, the indicator will show the correct location. In this next segment, I'll demonstrate how the system detects rotational acceleration. First, I created a yaw rotation. As you can see, the alpha term on the app consists of roll, pitch, and yaw. In this case, the yaw acceleration is 7.3 radian per second squared. Meanwhile, the color mapping shows the weight of the helmet, which is at the top of the head. Then, I'll introduce a pitch rotation to the helmet. For this instance, the pitch acceleration is 3.43 radian per second squared. Finally, I'll introduce a roll rotation to the helmet. A roll acceleration of 3.08 radian per second squared was detected. Due to the pandemic, we couldn't perform job tests to evaluate the accuracy of the FSR matrix. Also, we couldn't use the rate table to evaluate the accuracy of the IMU. A different sensor range must be considered, as in real application, the impact severity may vary. To commercialize the product, implement PCB design with flat flex ribbon jumpers will provide a neat design. An ergonomically designed toque or helmet that consists of the design head impact telemetry system is very important. Finally, an iOS-based app should be developed to make the product more practical. Thank you for watching.